Okay, let's continue our discussion about example 5.11. So here's the circuit geometry. You have a magnetic core in this shape, and it has three legs with a gap in the mid on the side, and you have a driven current source in the middle. So you are asked to find the NI required to achieve magnetic flux across the gap. So let's write up the essential equation relationship of the magnetic flux 5 and the so-called voltage drop, like the potential drop comparing to electrical circuit. So here you have a simple relationship like this. So from at this node, you know the influx of the magnetic flux goes into the node is phi 2, and the magnetic flux going out of the node is phi 1 and phi 3, and the amount of magnetic flux goes into and goes out of the node should be the same. So you can write up the relationship of phi 2 equals to phi 1 plus phi 3. This is pretty much the same as KCL, Kirchhoff circuit law, KCL. So if you comparing the magnetic circuit with electrical circuit, the Norton theory, that is, the currents goes into and out of a node is the same, still valid. The only difference is the electrical current is replaced with magnetic flux phi. So you have phi 2 equals to phi 1 plus phi 3. And another relationship you can write up in terms of phi is the continuity of the magnetic flux across the gap. So phi 3, the amount of phi 3 should be the same of phi g that goes across the gap. And similarly, using the Kirchhoff voltage law, that is the Thevenin theory. For electrical circuit, you can find out the voltage rise at the voltage source shall equal to the voltage drop on different places of the electrical circuit. Similarly, the potential increase, say Ni, shall equals to the drop due to the magnetic field times the length L. Magnetic field intensity H times the length L. So in the middle, the potential is the potential drop is H2 times L2. And if you go to the loop to the right, you have H2 times L2, H3 times L3, and Hg times Lg. So the three terms complete the circulation on the right leg. And if you look at the circulation of the potential, magnetic potential in the left, you can have Ni equals to H2 times L2 plus H1 times L1. So it's similar to the Kirchhoff voltage law. And if you compare the two equations, you can simplify the two equations with H1 L1 equals to H3 L3 plus Hg Lg. Alright, so you have a couple of equations at hand, and we can substitute our knowledge about the circuit to solve this problem. The first thing is the magnetic flux density. Magnetic flux get across the gap area. All right, and here's an interesting concept. In this case, to be realistic, to approximate the actual scenario, we say that in leg 3 of this ferromagnetic material, most of the magnetic flux phi is confined within this rectangular region. However, as it gets across the gap, the distribution of magnetic flux will spread a little bit to the side. 老实讲啊，你这个东西去考量进去是比较真实一点的，当然其他对于答案的结果差别一点点的，没有很大哦。不过没关系，我们还是照着课本上所讲的哦，去看一下这一个状况哈。Alright, so the problem, the textbook says to address the influence of the spread of the magnetic field, we assume that the magnetic field only spread with in this region, which is about half of the gap size. So it's the width of this region is Lg over 2. Now, Lg is the length of the gap. So if the gap becomes larger, there will be more spread of the magnetic flux in the neighborhood. So if the gap is relatively small, then most of the magnetic flux is still confined within the ferromagnetic, the magnet's region and experience less spread. But anyway, we assume that in this dash line region, which is slightly larger than the cross-section area of the leg 3, and it can be the size of leg 3, say square root of, suppose that it's a square cross-section area, then the size, the length of the side of this dash square is square root of 3 plus Lg, which has, you will count the spreads on the two sides. Each side is Lg over 2. So the two sides combined is Lg. So the area, the effective cross-section area in the gap region is slightly larger than the third leg, which is 3 centimeters square. Now, considering the spread, the effective cross-section area is 3.07 centimeters square. By substitute Lg as what? As 0.2 or 0.02. 0.02, okay, 0.02, right? 所以它多了多少？多了2%了，那个面积大了2%，所以那个场墙会稍微弱一点点啊。假如你不考虑的话，那个场墙会高2%哈。但你考虑的话，那个场墙因为面积变大了，所以它的那个 Hg 哈会小一点。All right, and next we can calculate the magnetic flux in this gap area. The total magnetic flux in this gap area should be the product of the area, which is 3.07 centimeter to the square, as we have already computed, times the magnetic flux density Bm in this gap area, and the total magnetic flux phi, as specified by the problem, is 4 times 10 to the minus 4. So this thing is the magnetic flux given by the problem. So by using the relationship using the known parameter and the calculated area size, we found the magnetic flux density required at the gap area is about 1.3 rep per meter square. Okay? And the corresponding magnetic field intensity at the gap region Hg can be found by which relationship? This relationship. Bg equals to mu sub 0. What is this? The permeability in the air times Hg. What is H mu sub 0? The permeability of free space is about 4 pi times 10 to the minus 12。好了，当然我教了10几年，这个数字是背得下来的哈。你大概背不起来没关系啦，那个题目上面会给你这个数字了哦。多看几遍能够背下来最好，当然我也觉得没有必要硬背了哈，只要是表上查得到的东西。Alright, so taking into account the permeability of free space and the required magnetic flux density, you end up with Hg, that is 0.1, 0.3737 times 10 to the 7th. That is the magnetic field intensity at the gap. Alright, using this knowledge, we can try to find out the magnetic flux density and the magnetic field intensity at the other parts of the circuit. And here's the interesting one. It comes with this figure. So what is the significance of this figure? This figure tells you that the permeability and the permittivity, the permeability, the magnetic flux density and the magnetic field intensity B and H, the relationship between the two is not linear in magnetic material. 在磁性材料里头，磁场强度跟磁通量密度的关系是非线性的。像在真空里头的话，这边写的 Bg 就是 μ0 Hg， 所以要告诉你的时候，因为 μ0 是一个常数，所以 Bg 跟 Hg 在真空里头，在非磁性材料里头，你的磁场强度跟磁通量密度的关系是线性的。但是在磁性材料里头，就像那一张图所给的，它是非线性的。这里头你会看到磁场强度 H 跟磁通量 B 的那个关系，磁通量密度 B 的关系是一条弧线。那这条弧线代表的是什么？这条弧线的斜率代表的是什么？代表的就是那个μ值。所以你会看到这个地方的斜率比较大，这个地方斜率比较小。到这边的时候，斜率几乎为0。所以这是磁性材料的一个特性。一开始的时候，μ值是比较大的，斜率比较大。也就是说，当你的磁场强度稍微提升，它在磁通量密度上面的提升是比较显著的。但是当你的磁场强度继续提升之后，这个斜率就没有那么斜了。也就是说，磁通量密度还会提升，但是没有那么的兴奋了。当你的磁场强度进一步提升，提到这个 region 的时候，磁通量密度只有微微的上升了，没得差小离啊，所以这个东西，这个第3个阶段叫什么 ？saturation， 或者说磁饱和的状态。所以对于磁铁这些材料来讲，它有所谓的磁饱和的特性。或许另外一个图你可能比较有印象的，不知道你有没有印象，就是这一个 hysteria， 我忘记名字了这个叫什么磁质曲线呢？在描述磁铁的特性的时候，我们有讲过磁质曲线，所以一些磁性材料一个很早期很基本的应用就是拿来做记忆体嘛。 为什么？因为你把磁场强度拉高以后，磁通量密度变大，但是你把磁场强度收掉之后，它的那个磁性还在那边。所以那个磁带啊，或者是说硬碟啊，早期的硬碟都是用磁性材料，不是早期的硬碟，现在的硬碟也一样是用磁性材料做的。有些用到磁性材料，用的就是磁质的那个特性。也就是说，磁场你移除磁场，但是它里头的磁区被磁极化之后的那个效果，不会因为你外加磁场的消失而改变，还会留一些在那边所以叫磁质曲线。那这里头你会看到的就是真实的磁铁，它们的磁场强度跟磁通量密度的反应关系不是线性的。磁场强度比较小的时候，那个μ值是比较大的；磁场强度在比较高的区域的时候，那个μ值就比较平滑、比较小。所以在刚刚的那个 Hg 跟 Bg 的计算里头，你可以直接用μ0，因为它是常数，非磁性材料是常数，直接用那一个 B 等于μ times H 的关系把它乘出来。但是在这一个磁铁线圈的这一个结构里头的时候，你的各个角位，各个 L1、L2、L3 这三只角上面的磁场跟磁通量密度的关系，就要利用到这张图了。Okay? Alright, so let's begin with the computation of magnetic flux density and magnetic field intensity in leg 3. Alright? Because what? Because we already found out the magnetic flux density Bg. And from the equations above, we have Bg equals to phi g. The total magnetic flux across on the cell leg is the same as the total magnetic flux phi g on the gap area. So phi 3 equals to phi g, which is 4 times 10 to the 4 minus 4. And B3, the magnetic flux density on the cell leg, can be found by dividing phi 3 over A3, which is 3 times 10 to the minus 4, the cross-section area of the cell leg. And you end up with a value of 1.33 rep per meter square. This is the magnetic flux density within the cell leg. So the next thing is to find out the corresponding magnetic field intensity H3 using B3, which is 1.33, and this figure. So here we want to find out corresponding H3 using B3. So B3 is what? B3 is 1.33. So you begin with this. You identify, this is somewhere close to 1.33. 当然我知道各位同学的眼睛因为看手机看太多，可能不是很准确啦所以我在改这一题的时候呢，不会跟你太计较只要你在这一点，你的那个 1.3 大概画在这个区域这两个区域里面，我大概都 OK 啦但是你假如说算出来是 1.3， 就你给我对到这边或对到这边，那就有点太过分了那当然这条线只画到大概250啦，但你可以自己再稍微延伸一下不一定有的时候因为题目每年会改搞不好你可能算到更小的值，你就自己延伸一下吧，好不好？稍微对一下了Alright, so using the figure, you can identify that the 1.33 magnetic flux density B is somewhere around 500, right? But in the textbook, this corresponding point is found to be 475, right? Okay, 475. So you can see the corresponding magnetic field intensity H3 is about 475, which is much smaller than the magnetic field intensity at the gap, which is Hg is about 0.1 times 10 to the 7th, which is about 1,000 times greater than H3. So why? Because of the difference in the permeability mu. Okay, so the permeability mu here is much larger. It's much larger in the ferromagnetic material. All right, so we have B3 and H3, and we would like to find out the B and H at the other location, H1, B1, H2, B2. So we can use this equation, H1, L1 equals to H3 times L3 plus Hg times Lg, because we already know L3, Lg, Hg, and H3. So you substitute all the known number within this equation, and you end up with H1, L1, the magnetic field, the H1, L1 product is 302.4 amp. In the first leg, and use this relationship, and you can find out the magnetic field intensity H1 by dividing 302 over 0.2, which is what? Which is the length of the first leg. It's 20 centimeters. So you substitute with 0.2 here, and you end up with a number of 1500. 1512, around 1500. And what is the next thing is to find out corresponding magnetic field flux density B1 using H1. Again, you will use this plot. So here you begin with H, because you already know the H, you don't know B. So you begin with H and find out the corresponding B value. So using the number 1512, which is around here, a little bit larger than 1500, and to this point is about what? 1.55 or 1.6. Yeah, so anything between 1.5 to 1.7 should be okay. All right, so here you have 1.56. All right, so you can use this figure to find the corresponding B from H, or find B from H from B. All right. So once you have B1, H1, you can find out the magnetic flux in the first leg, which is the product of B1, A1. All right. So you have this number, 4.68 times 10 to the minus 4, which is a little bit larger than the magnetic flux in the third leg. Anything else? Yeah, we need to find out B2, H2, and Phi2, right? The things in the middle leg. What do you think of the B, H, and Phi in the middle? Well, we can first find Phi2 by what? By taking the summation of Phi1 and Phi3, because of the Newton theory, right? KCL. So Phi1 is 4.68 and Phi3 is 4, so the total magnetic flux Phi2 is 8.68 times 10 to the minus 4. The magnetic flux density in leg 2 is Phi2 over A2, which is this number divided by 6 centimeters squared, which equals to 6 times 10 to the minus 4 meters squared. So you end up with a number of 1.447. And you want to find out H2. So again, we will use this figure. Begin from B, which is 1.447, which is around here. And with this figure, you can end up with something like 750, right? 750. So this is the magnetic field intensity in the middle leg. So again, for ferromagnetic material, ferrite, the relationship between H and B is nonlinear. The slope, the permeability is larger with a low magnetic field intensity and becomes smaller. Mu value becomes smaller with a large magnetic field intensity, right? And the Ni required to produce the magnetic flux within the structure can be found by using this equation or the other one. Ni equals to H2L2 plus H1L1 or H2L2 plus H3L3 plus HGLG. They shall give you the same result. And by substitute the side, the value of the magnetic field intensity and length of the leg of the circuit, you have something like a 377 amp. Right? So if I specify that the number of turns is 100 turns, then what is the current required for this source? 3.7 amp. All right? Something like that. Okay, so here's the derivation of the solution of this problem. And the very last thing we'd like to discuss for this problem is the calculation of the reluctance. So as we have seen in the previous slides, the reluctance is defined as the length over permeability and the concession area. So it's L1 over mu1 A1. And mu1 can be substituted with H1 over B1, right? The ratio between magnetic flux density B over magnetic field intensity H is the value of the permeability. So for magnetic material, it changes as the magnetic field intensity H changes. All right. So using this definition, you can substitute the known number to find out the magnetic flux, the reluctance of the magnetic circuit. And as you can see, you have some large number. All right, for arch. So by looking at all those numbers, which one is the smallest? Well, R2 is the smallest. Why? It's only in the order of 86,000. It's about 86,000. Why? Why this one is the smallest? Well, because the concession area is twice as large as the other two, right? Another thing you can notice that is R1 is much smaller, much larger than this one. And RG is about the same as R1. Why? Because at the air gap, the permeability is relatively small. So it produces a lot of resistance or reluctance for a magnetic circuit. So it becomes more difficult to get across the air gap. Because the smaller magnetic, the small permeability. That's the reason why the reluctance at the gap is relatively large. And because of the large reluctance in leg 3, because RG is connected to in series with R3, so the current or the magnetic flux going to the right is relatively small. Therefore, R3 is relatively small, is somewhat smaller than R1, even though that L1 and L3 are of the same length. However, because the magnetic flux in L3 in the right leg is much smaller, so the mu value is larger. Okay, mu value is actually larger than mu 3 is actually larger than mu 1. So it's resulting in smaller reluctance in leg 3, but you have a larger reluctance in leg 1. Right, so that should conclude our discussion about section 5.6. So the very last section is 5.7. I'm not sure that I can finish up today, but anyway, we we can finish it on Tuesday. But anyway, let's begin with our discussion with section 5.7. Electromagnetic energy conversion, which is an interesting topic. So in this section, we are looking into the conversion of energy, including electromagnetic energy, electrical energy, and mechanical energy. So we are dealing with mechanical energy, electrical energy, and electromagnetic energy. So what is the difference between electrical energy and electromagnetic energy? Well, when it comes to electrical energy, you are talking about voltage and current. And when it comes to electromagnetic energy, you are talking about electrical field intensity and magnetic field intensity. OK， 好，所以在我们在讲的是电磁场的能量跟电能的时候，你大概可以这样做区分嘛，电能指的是电压电流的形式所储存的能量。电池的能量指的是以电场、磁场的形式所储存的能量。那这边另外一个牵扯到的是机械能所以机械能包含我们这边看到的是位能虽然说机械能其实另外一个机械能来源是动能，但是在这边我为了让题目的讨论比较简化一点，所以这边所讨论的机械能并没有讨论到动能，也就是说我们不去讨论一个有明显速度的移动物体啦我们这边讨论的大概是因为重力所造成的机械位能。OK， so first let's look at the figure representing the problem. So in this problem, we have two plates like a capacitor, two parallel plates. One is a fixed. The bottom one is fixed at position of x equal to 0 or something like that. And the top plate is movable, goes up and down. And because it is, as you know, this is a capacitive structure. So if you apply a voltage source, the two parallel plates, the two conductors should build up some charge on the top and bottom plate. And because of the polarity of the voltage source, you have positive charge on the top plate and negative charge on the bottom plate. So, and they are of the same magnitude. So you have Q on the top and minus Q in the bottom. And the charge distribution across the parallel plate configuration establish a magnetic field Fe, a magnetic field E, field intensity E, and the presence of E and charge produce the electrical force as Coulomb's law, due to the Coulomb's law. F equals to what? QE, right? 电场作用力当你有电荷又有电场的时候呢，它就产生电场作用力 F 所以我们用一个下标 E 来表示它是电场作用力。然后在这里头，你是上面正电荷，下面负电荷，所以是相吸的嘛，所以它的电场作用力方向是往下的，所以会把上板往下拖，因为有带电荷的关系，所以电场作用力会让平板移动。只要你没有任何外力去阻挡它移动的话，它就会掉下来 keep 就会，对吧？好。So if you apply a voltage source, you accumulate positive and negative charge on the two plates. You will produce electrical field force, electrical force. The electrical force Fe will produce a placement, 一个位移that moves the plate from will move down the plate, right? And it shall convert the electrical energy into mechanical one. And considering that if the parallel plate is infinitely large, Of course, there is no infinitely large parallel plate, but providing that the gap between the two plates is small, you can approximate the problem as nearly infinitely large parallel plate, and the consequence of this assumption is that the electrical field intensity built up within the structure is indifferent to the position 所以假设这一个平板电容结构那个板子的面积够大，间距够小的话，那么在其间的电场分布是均匀的所以电场强度不会因为你比较靠着上板或比较靠着下板而有所差距所以它有一个均匀的电场可以建立在两板之间所以假如这个图跟前面那个图差别在哪里 ？What is the difference between this figure and the previous one? In the previous one, you have a battery, a voltage source, which can provide additional charge or absorb additional charge. However, in this figure, you don't have a battery. That means the amount of electrical charge Q remains the same no matter you move up or move down the top plate. In other words, if you move the top plates further up, you will what? The voltage difference between the two becomes even larger because the electrical field intensity E remains the same between the two plates. So if the distance becomes larger and larger, the voltage difference, which is the product of V and D, E and D, becomes larger. So in this scenario, if you move out of plates, you will what? You will build up the amount of electrical energy. And the way that you can increase the amount of electrical energy stored in this structure is because you move the top plates up, because you input more mechanical energy into the structure. So you should already notice that there is a balance between mechanical energy in terms of potential and the electrical energy in terms of the Q or the electrical charge or electrical field stored in this structure. So in this case, you can convert mechanical energy into electrical energy by moving the top plates up and down. And in the previous case, you can convert electrical energy into mechanical energy by applying a voltage source, by electrical energy source. All right, so here is a diagram to show you the energy involved within this scenario. To complete the description of this problem, it actually has 5 terms. The mechanical energy input to the left, the electrical energy input to the left. You can see that the mechanical energy is provided by the main power, your hand. And the electrical energy is provided by what? By the battery. And to the right, you have 3 terms to consume the energy. One is due to friction or due to energy dissipation, like the thermal energy dissipation. Well, it's a little bit complicated for students in the EE department, so let's ignore it. And the increased stored mechanical energy in terms of velocity, right? It's a little bit difficult for EE students, and ME students. So let's neglect it, assuming that the velocity of the moving plate is relatively small. So if you if you cross out the two terms, you have only terms here is the electrical store energy. The store electrical energy increased. That is the electrical energy stored in the structure. All right. So here, if you have this is a lossless system, so the very last term on the right is eliminated, and if you assume that the speed or the velocity of the moving place is very, very small, the speed is nearly zero, then you don't accumulate mechanical energy in terms of momentum. So you have only three terms in this structure, right? So we will need to look at the three terms in different situations. If there is no battery applied, the amount of electrical charge stored in the two plates does not vary. So the external force, external mechanical energy input will produce more stored electrical energy within this structure. So you can see this is the mechanic force. This is the increase of electrical energy in the parallel plate. This one is the energy stored in the battery because we do not attach the battery. So this term is not involved in this relationship. That's what happened in the previous slide. And here's another case. If you apply the voltage source, if you attach the battery to the circuit, and you may have stored electrical energy in terms of WE. WE refers to the electrical energy stored in terms of electrical field. So WE refers to the electrical energy stored in the structure here. 所以 WE 指的是粉红色这一块这一块是结构所储存的电能。因为结构本身的那个储存电能的能力是由它的结构的电容值 C 所界定嘛，所以 C 值是固定 ，C 值是根据那个间距固定的，然后 C 值再乘上电压的平方除以2，就是储存在结构里头的电能，而电池或者是电源所提供的电能，也就是电池的那个电能是 VI 抵 T，VI 是功率啦 ，VI 是功率嘛，乘上时间就变成是功 ，OK， 所以这个单位是功这个注意你自己注意一下，这个式子的单位是功，所以最左边是机械能W 等于 Fs， 力量乘以距离。也就是机械能所做的功，力量乘以位移，板子上下移动的距离，那这个负号其实是代表它是提供能量或者是减少能量了，跟你的那个位移是变多还是变少有关。好，所以在这一页里头，当然这几页有点花啦，所以你回去的时候要多看几次，好不好？搞清楚这边的 WE 啊，还有什么 FEX 啊，它们代表的意义，好不好？所以 WE 指的是什么 ？WE 是储存在结构的电能等于1/2的 CV 平方，然后 V 又可以用什么？用那个 V 除上 X 的话，就可以变成是电场，变成是电场，所以这个式子整理 C 等于 Epsilon A over X， 所以整理一下的话，你可以得到 WE 等于是 Epsilon 0 V 平方电压平方乘上 A 除上2倍的 X， 也就是你的那个间距。所以 dWE over dx 对 x 方向做微分的话，可以得到 可得到这个关系啊，所以你自己记得做一下公式那个式子的推演啊，所以这个对 x 微分之后变成这个东西。而你的电荷量 Q 呢会等于 CV 值嘛，哈，这是 by definition 哈。那我们这边其实已经有 V 的表示式了哈，有 C 的表示式，所以你可以得到这个关系式。所以 dq dx 也就是说，这块板子上下变动的时候，它对于电荷数量的改变哈，所以这是 dq dx 的关系式哈。而这些关系式呢，从这边过来的又可以去对应到 F1x。好，所以 F1x 把 W 对 x 做微分，把 Q 对 x 做微分，哈，可以得到你的 F1x， 也就是机械力的那个大小。啊，所以这边把这些结果套进来之后，你可以算出来它所对应的那个 external 的 electrical mechanical force F1x 等于-1 Q square over A epsilon sub 0。啊。而这个力量是要往上提的哈，才能够避免那块板子掉下来。OK， 好，那这边我们来看一下，假如上面这个 case 是有接电池的，然后这个时候你只要把电池拿掉啊 ，if no voltage source is applied, Q was held as a constant, so dq over dx equals to 0. Then the second term to the right is eliminated. Then F1x is proportional to the WE over dx, the WE over dx. So by substituting the WE within this equation and taking the derivative in terms of x, you end up with this value. So here is the electrical force required if no battery is attached to this parallel plate structure. So as you can see, the implication of this result is the larger the electrical charge on the plate, the required mechanical force is larger. The mechanical force required is proportional to the square of electrical charge on the plate. 你会看到它是一个 Q 平方的关系式。所以你看到这边的 F1x 表示是在没有电池的情况下，跟有电池的情况下，虽然说是类似的但是它所牵扯到的那个结构内的电能跟电池内的电能是不太一样的所以到这边其实有点花了所以我们快速的看一下 example 5.12， 那它可以让你去看到。所以5.12你还是要看过看已经来不及了。好，下礼拜再讲5.12好了。OK， 好了，我们今天先到这边。